Hello again. In this segment, we'll talk about graph traversals. Traversal means visiting every single node exactly once. Traversal is a little different for both trees and graphs. For trees, we start at the root and then recursively keep going down until we reach the leaves. Whereas for the graphs, there is no apparent order. There is no notion of start or end. It may also have loops and cycles. These properties make graph traversals more challenging. So before we begin, we need to define some terms. A node that is unexplored is shown by an empty circle. A node that is visited is shown by a blue dot over the circle. An unexplored edge is a thin line between nodes. A discovery edge is an edge between a visited node and an unexplored node. This is shown by a thick greenish line. A cross edge is an edge between two visited nodes. This is represented by a reddish line. Now, with the definitions out of the way, we are ready to do a breadth-first traversal on this graph. On the left side, you see a simple undirected graph, and on the right side, you see its adjacency list. Just like the trees, we need a queue to perform a breadth-first traversal on the graph. The state of the queue is shown by dotted lines at the bottom of the screen. Let's say we start from vertex A. We immediately marked it visited and put it into the queue. Then we dequeue A. Note carefully that the edge AB will be marked as a discovery edge because according to our definition, A is visited and B is still unexplored. As soon as B is added to the queue, it becomes a visited node. We repeat this process for all of the incident vertices of A, marking edges AC and AD as discovery edges. We also add C and D to the queue and mark them visited. At this point, B is on the front and will be dequeued next. As soon as B is dequeued, its adjacent vertices are added to the queue. Here A will not be added because it's already visited. C will not be added because it's already present in the queue. Note here that the edge BC will be marked as a cross edge because both B and C were already explored. If there is even one cross edge, that means the graph has a cycle. E is unexplored, so we add it to the queue and mark the edge BE as a discovery edge. Now we remove C and add its adjacent vertices to the queue. A and B are already explored, so we won't add these to the queue. D and E are already in the queue, so we won't add these again. Note that the edges CD and CE are marked as cross edges. The only adjacent vertex F is unexplored, so we mark the edge CF as discovery and add F to the queue. We dequeue D and add its unexplored adjacent vertices to the queue. The only available is H, so we mark the edge DF as a cross and DH as discovery. H is also marked as visited. Now removing E and adding G to the queue. B was visited earlier. C and F are already present in the queue, so we don't want to add these again. We mark the edge EG as a discovery edge. Now remove F. All of its adjacent vertices are already visited, so nothing new goes to the queue. Here we mark the edge FG as a cross edge. Removing edge adds nothing new to the queue. The edge GH is marked as a cross edge. Finally, we remove G. The queue is empty and the algorithm stops. Here, the thick discovery edges make up a spanning tree. This is one of the many possible spanning trees for this graph. A spanning tree is just a subset of a graph that contains all the vertices and has no cycles. If you add the adjacent nodes to the queue in a different order, you'll end up with an entirely different spanning tree. The starting node also matters. It becomes the root of the spanning tree. If the graph has even one cross edge, it means the graph has cycles. In the next segment, we'll explore source code for the breadth first search or the breadth first traversal.